So in the last video, I kind of left off by saying that our confidence interval has two pieces. The first one we call a point estimate, and then we add and subtract, so we plus or minus a margin of error. So if we're trying to estimate the population proportion, the value that we're going to use for the point estimate is p hat. So this would be the proportion that we get from a sample of a certain size. And so from that we'll take plus or minus e. That's the symbol that I'm using for margin of error. And I mentioned that margin of error is calculated. It's the product of these two pieces. One is a critical value, and the other is a standard error. And the standard error is the error in the sampling distribution. And we've learned that that, in this case, is the square root of p times 1 minus p all over n. And this critical value is actually going to be a z-score. One thing adjustment that I need to make before I move on. So remember, our whole goal here is to estimate p. And notice that I've used p twice in this formula. Well, if I knew the value of p, I wouldn't need to estimate it. So the whole point here is that this is what I would like to know, but I'm not going to be able to use p in this calculation. I'll have to just make do by using p hat to calculate the standard error. So when I calculate the sample proportion, and by the way, just as a reminder, the sample proportion would be the count, how many in your sample have a certain characteristic, divided by the sample size. So I would calculate this, and I would use that then to calculate the standard error. Now, what about the z-score? So in the previous example, I said that I wanted to capture 95, or I wanted 95% of my intervals to capture the mean. So, and then I used 2 for this z-score. Now, let me kind of explain, and actually I'm going to amend this a little bit. The way that we're going to find this critical value is to look at our standard normal distribution. So this is our distribution that centers at 0 with standard deviation of 1. So this is -1, -2, and -3. And let's think, if I want to capture the middle 95%, so I know that that goes pretty much from -2 up to +2, but between there and there is 95% of my p hat values. Now, if we were to, I know that the entire curve, that's 100%. Now, if you take away the middle 95, you're actually, left with 5%. And half of that is here in the left tail, so I'm going to color that in blue. And half of it is here in the right tail, also in blue. So I need to divide that by 2. And so you get 2.5%, or 0.025. That's in the left tail, 0.025, and in the right tail, 0.025. So to get a more accurate value for this z-score, we can use technology. For instance, if you have a TI-84, you would use your inverse norm function, which is in your distribution menu, and you would put in a probability and then 0 and 1. Now, in this case, the probability that I want to put in is this value here, 0.025. So I would take inverse norm, 0.025, 0, and 1, and I'm going to get a negative z-score. It's approximately negative 1.96, and so not exactly 2. 2 is what we use in the empirical rule. It's really close to this, but this is a more exact value, and it's common when we're looking for these critical values in this context to take the absolute value here. So just take 1.96. So really in practice, if I wanted to speak about 95% in a confidence interval, the critical value that I would use would be 1.96. And if you wanted a different confidence level, so for instance, maybe I wanted to be 90%, say I was capturing 90% of the sample proportions, or if I want to have a 90% confidence, then I'm thinking to myself, okay, let's think about a normal distribution where we take away the middle 90%. So if there's 90% in the middle, that means there's 10% that has to be split with 5% on each of these sides, so 5% in each tail. Notice that those three things add up to 100. Now, to find the z-score, the critical value that isolates 5% in the left tail or 5% in the right tail, these are just going to be opposite one another. This is going to be negative and this is going to be a positive value. Then I can use that inverse norm and 0.05, 0 and 1. And in that case, you're going to get 1.645. Now, if you put in this value, you'll get negative. If you were to look at the right-hand tail, that would be positive. Either way, we say for a critical value, it's 1.645. It's convenient to just have some of these values memorized. So if you have for confidence level in statistics, we'll use the letter C. So to find other critical values, we will take 1 minus C, and we call this value alpha. That's the level of significance. And then we'll use our inverse norm function with alpha over 2, 0, and 1. And this will give us z. And we use a subgroup of alpha over 2 just to note that this is, if we're taking, for instance, why does this make sense? Let's say if you wanted 99% confidence. When I take 1 minus 99%, I get 0.01 or 1%. And so that's what I'm taking, that's the level of significance. But that has to be split between the two tails. That's why we take it over 2. So 0.01 over 2 is 0.005. So this is 0.005 in this tail, and this is 0.005 in this tail. So for a 99% confidence, I would want to find this z-score, and so I will use my inverse norm, 0.005, 0, and 1, and you'll find that that is 2.576. And so 2.576, and that's the absolute value of that. So we've already found this for 95%. We use 1.96, and for 90%, we can use 1.645. I'll add another one in here. 98%, you can use 2.33. So these are our critical values, z of alpha over 2. So putting this all together, to construct our confidence interval, we'll take a p hat plus or minus e. And that's our margin of error. So p hat plus or minus z of alpha over 2 times the square root of p hat 1 minus p hat all over n. So this is the point estimate, the critical value, and this is the standard error. And so those are the pieces of the confidence interval. Now, when we usually, or oftentimes, we'll write the confidence interval as an interval where there's a lower bound and an upper bound. And so this would be p hat minus e, and this would be p hat plus e. Conveniently, a TI-84 will do a lot of this work for us. So let's say that we are taking a samples of size 1,000, and in the sample we find that 515 people have a characteristic that's of interest to us. Maybe they are going to vote for a certain candidate out of 1,000 people. And we want to construct a 95% confidence interval. So if you go to your calculator and to the distribution menu, to the stat menu, scroll over to the test, and you can scroll up or down. It's actually a little bit faster, I think, to scroll up in this case. But I want to choose this 1 proportion z interval. And so I'll hit enter, and I'm just going to clear all this out. I'll just type over it. So in this case, I'm saying that I had 515 in my sample with this certain characteristic. That was out of 1,000. I want to be 95% confident. Now, don't put a decimal here. The confidence level in your calculator, you can just type in 95. You don't have to type in 95% nor 0.95, and we can calculate. And notice that it gives me a lower bound and an upper bound, and then the p hat value. So the lower bound is 0.48402. The upper bound is 0.54598, and we're told that p hat was 0.515. So that's nice. One piece of information that's missing here, though, is what exactly is the margin of error. So remember that this is symmetric. That's p hat plus or minus e. So if you take one of these values, so for instance the upper bound here, 0.54598, and subtract p hat, 0.515. Let me just kind of, so I took 0.54598 and I subtract 0.515. So the answer that I'm getting is 0.03098. Now, think about on a number line what's going on here. So I have my 0.515 here in the middle, and then there's 0.48402. And somewhere up here is 0.54598. And this distance from here to here is E, and this distance from here to here is E. So this in the middle is my p hat. So that was plus E, and that's minus E. So notice these are the same. So here I was suggesting that we take this value and subtract that, and see how that's going to give us E, our margin of error. So the margin of error here would be about, we'll say 3%. So our estimate is about 51.5%, and our margin of error is 3%. So how do we interpret a result like this? We can say that we are, in this case, 95% confident the population proportion. And if you have some context, we would write it in here. So for instance, if this was the proportion of people who we expected to vote for candidate A, the population proportion who will vote for candidate A is between what? Let's see, that was 48.4% and 54 if I'm rounding here, I should probably go up to 6%. All right. So I am going to pause here for this video, and I have a couple of other things to add on this, and I'll just do that in part 3.